To understand the cosmic horizon and the regions beyond it, we first need to clarify what the term horizon means when applied to the universe. Most of us are familiar with horizons on Earth, the line where the sky appears to meet the ground or sea. The cosmic horizon operates on a similar idea, but instead of marking the limits of our vision caused by the Earth's curvature, it marks the limit of our observable universe. This boundary defines what we can potentially see and study, not because of any physical wall, but due to the finite speed of light and the expanding nature of the universe. Light travels extremely fast, approximately 299,792 kilometers per second, 186,282 miles per second. But the universe is also exceptionally vast. The light from distant objects takes time to reach us. This means when we observe stars, galaxies, or cosmic events, we see them as they were in the past. The farther away an object is, the older the light we receive from it. For instance, when you look at the sun, you see it as it was about 8 minutes ago because that's how long sunlight takes to reach Earth. For stars beyond our galaxy, we see them as they were years, millions of years, or even billions of years ago. However, this process has a limit. Since the universe is about 13.8 billion years old, one might initially think that the maximum distance we can see would correspond simply to 13.8 billion light-years. The distance light could travel in that time. But the expanding nature of space complicates this calculation. The universe has not been static as light traveled. It has been stretching and growing, meaning objects that emitted the light we now observe were much closer when that light started its journey, but have since moved much farther away due to cosmic expansion. Consequently, the observable universe extends well beyond 13.8 billion light-years in radius. According to current measurements and cosmological models, the radius of the observable universe is about 46 billion light-years, making the diameter about 92 billion light-years. This boundary or limit is what we call the cosmic horizon. It represents the maximum distance from which information, primarily electromagnetic radiation like visible light, radio waves, or cosmic microwave background photons, can have reached us since the beginning of the universe. But what happens beyond this cosmic horizon? It might be tempting to picture the universe as a giant sphere with a wall or edge at the horizon, but that's not the case. Instead, the cosmic horizon is more like a limit of visibility imposed by the finite age of the universe and the speed of light, combined with the effect of expansion. Beyond this horizon exists space, and probably an enormous amount of matter and energy. But these regions are effectively hidden from us because the light, or any signals from those regions, has not had enough time to travel across the expanding cosmos to reach us yet. This concept introduces a fascinating aspect of cosmic observation. No matter how powerful our telescopes become, there will always be areas of the universe forever beyond our reach. We cannot gain information about what lies past the cosmic horizon, at least with observations relying solely on light or another form of electromagnetic radiation. To put it plainly, the cosmic horizon acts as a kind of cosmic limit box constraining our view and knowledge of the entire universe. The idea of a cosmic horizon is closely tied to the Big Bang model of cosmology and the measurement of the cosmic microwave background, CMB. The CMB is a faint glow of radiation that fills the universe and serves as the afterglow, from when the universe was just about 380,000 years old, shortly after the Big Bang. It is the oldest light we can observe, offering a snapshot of the universe at a very young age. The CMB itself forms a spherical surface of last scattering that defines the observable universe because radiation emitted before this epoch was effectively trapped inside an opaque plasma of charged particles and could not travel freely. Scientists study the CMB and distant galaxies to better understand the early universe and to estimate cosmological parameters such as the expansion rate known as the Hubble constant, the density of matter and dark energy, and the universe's geometry and fate. These studies inform our understanding of the cosmic horizon by refining the scale and nature of the observable universe. At the same time, the expanding universe means that some regions are receding from us faster than the speed of light due to the expansion of space itself, a phenomenon allowed by the rules of general relativity, without violating the cosmic speed limit for objects moving through space. This leads to an event horizon beyond which light emitted now will never reach us in the future, indicating not just a horizon tied to the finite age of the universe, but also a cosmic event horizon that limits future observational possibilities. The cosmic event horizon is particularly relevant when considering the role of dark energy, the mysterious force thought to be driving the accelerated expansion of the universe. Because of this acceleration, some regions of space are moving away faster and faster, outpacing the ability of their light to ever cross the intervening space toward us. As a result, certain distant galaxies will eventually fade from our view, not because they suddenly disappear, but because the space between us expands too rapidly for their light to ever reach Earth. So, there are two horizons. One that defines the boundary of our observable past. The cosmic microwave background sets a firm window into the early universe, and a future event horizon that limits what we will ever be able to observe or interact with going forward. Between these horizons lie countless galaxies, stars, and cosmic phenomena, most of which we can see, and countless others, currently hidden beyond our observational limit. Delving into what might exist beyond our cosmic horizon, it's important to note that current cosmological models suggest the universe beyond the observable part likely bears similar characteristics to what we can observe. Vast collections of galaxies, dark matter, and energy, all part of a larger cosmic system. The universe, as far as we know, continues beyond our sight, possibly infinitely. But without observational data from those regions, we base our assumptions on the principles of uniformity and isotropy. That on large scales, the universe looks the same in all directions with roughly the same physical laws applying everywhere. This brings subtle but important questions about cosmology and physics. If some regions of the universe are forever unreachable, how complete can our understanding of the cosmos be? Scientists face this limitation constantly, needing to infer the nature of the whole universe based only on what is observable. This challenge underlines the importance of studying the cosmic horizon itself and understanding expanding space, dark energy, and other cosmological phenomena. The cosmic horizon also shapes our understanding of time and observation, inspiring deep connections between astrophysics and the philosophy of science. For example, the fact that we look into the past as we look across distances means that studying the cosmic horizon is essentially studying cosmic history. It's not just about where things are, but when and how the universe evolved. In summary, the cosmic horizon marks the farthest distance from which light and information have reached us since the Big Bang. Beyond that lies an unknown realm, abiding by the same physical laws but remaining forever inaccessible to observation, at least with existing physical principles and technologies. Exploring the mystery of what lies beyond this cosmic horizon involves piecing together a cosmic puzzle using the tools of theoretical physics, astrophysics, and cosmological observations. It's a frontier defined not by physical boundaries, but by the fundamental limits of observation and the interplay of cosmic time, light speed, and the ever-expanding fabric of space. Understanding the universe beyond the cosmic horizon requires us to consider not just what we see, but what we infer based on the principles that govern our cosmic neighborhood. One such principle is the cosmological principle, which posits that the universe, when looked at on sufficiently large scales, is homogeneous and isotropic. This means it appears roughly the same in every direction and at every location. Although this principle has limitations when examining small-scale structures like galaxies and clusters, where matter is clumped irregularly, it provides a powerful foundation to hypothesize about the unseen regions just beyond our horizon. If we accept that these conditions hold true not only in the observable universe, but beyond, the nature of those shadowed regions may closely resemble what astronomers and cosmologists observe nearby. The same atoms, galaxies, and dark energy that populate our cosmic neighborhood are likely spread throughout, suggesting a vast cosmic ocean stretching far beyond our sight. On a fundamental level, the same physical laws of gravity, electromagnetism, and quantum mechanics that explain phenomena we can study here would also apply there. One might wonder if the expansion of the universe implies a center from which everything moves outward, or an edge where the universe ends. Our current understanding, based on Einstein's theory of general relativity and meticulous observations, dispels both these ideas. The universe's expansion is not the outward motion of galaxies through space from a central point, but rather an expansion of space itself. Imagine the universe like the surface of a balloon being inflated. Galaxies move apart as the balloon's surface stretches, but no single point on the surface acts as a center or edge in the conventional sense. This balloon analogy also helps us grasp why the cosmic horizon is not a fixed boundary but can change over time. As the universe ages, light has more time to reach us from more distant regions, gradually enlarging the observable universe. However, the accelerated expansion driven by dark energy complicates this picture by causing some distant galaxies to recede so quickly that their light may never reach us, effectively pushing parts of the cosmos permanently beyond our grasp. Exploring the nature of these inaccessible regions touches on some of the most profound questions in cosmology. Can we ever learn what's truly out there? How do the laws of physics operate on scales and in environments beyond human reach? These questions drive theoretical models that go beyond direct observation. For example, the concept of the multiverse has entered scientific discussion as a possible explanation of various cosmic puzzles. Although this idea often finds itself in the realm of speculation, it stems from well-established equations and frameworks in cosmology, such as inflationary theory, a model that describes an extraordinarily rapid expansion of space in the first fractions of a second after the Big Bang. According to some versions of this theory, the universe we observe might be just one bubble in an enormous foam of universes, each with potentially different properties or physical laws. However, these scenarios remain speculative because, by definition, regions beyond our cosmic horizon provide no direct observational evidence. Without signals reaching us, no telescope or particle detector can confirm or refute their existence. Instead, cosmologists approach these ideas by scrutinizing the predictions they make for phenomena within our horizon, testing these predictions against observations. When theories align with observable data, they gain credibility, even if they say something about places we cannot see. Returning to the observable universe, the cosmic microwave background, CMB, offers a remarkable window into conditions near the cosmic horizon's edge. By measuring tiny fluctuations in the temperature and polarization of the CMB across the sky, scientists can trace the distribution of matter and energy shortly after the Big Bang. These fluctuations serve as seeds for the structure formation that leads to galaxies and clusters we see today. Advanced space-based missions, such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have provided detailed CMB maps that allow us to understand the universe's composition, age, and rate of expansion with unprecedented precision. These detailed observations also highlight how the universe itself can influence what lies beyond our horizon. The observed uniformity of the CMB across vast distances puzzles scientists because signals have not had enough time to balance out conditions across space regions, separated by more than the cosmic horizon, at the time the CMB was emitted. This observation supports the idea that an inflationary period must have occurred in the very early universe, rapidly stretching space and smoothing out irregularities, effectively connecting distant regions that would otherwise remain causally disconnected. Inflation theory thus provides both a mechanism to explain why the observable universe looks so uniform and a plausible reason to believe the universe extends far beyond what we can see, continuing smoothly into the hidden realms beyond the cosmic horizon. It implies that, although we cannot observe these regions directly, the same inflationary processes likely shape them, suggesting a vast, connected cosmic fabric. Yet questions remain about whether anything beyond the cosmic horizon could be fundamentally different, especially concerning the universe's geometry and fate. Is the universe flat, open, or closed? Current measurements, particularly those involving the CMB and the distribution of galaxies, strongly suggest that the universe is spatially flat or extremely close to it. This shape means that parallel lines remain parallel, and the universe could possibly extend infinitely. If this flatness and uniformity extend beyond the observable universe, it supports the notion that the cosmos is, on the whole, consistent throughout. But this conclusion comes with a caveat. We cannot confirm these properties beyond the horizon, and alternate geometries, while less supported, have not been entirely ruled out. Moreover, the nature and persistence of dark energy, responsible for accelerating the cosmic expansion, may influence the global topology and future of spacetime in ways still under investigation. Dark energy, despite constituting about 70% of the universe's energy content, remains one of the biggest enigmas in modern science. It behaves as a repulsive force, driving regions of space apart at an increasing rate. This acceleration shapes not only the cosmic horizon, but also how matter is distributed in the universe on the largest scales. As dark energy continues to dominate, galaxies beyond a certain distance become unreachable, isolated from us by the accelerating expansion. This accelerating expansion highlights an important and somewhat unsettling aspect of the cosmic horizon. The universe is becoming increasingly fragmented in terms of observations and interactions. Galaxies that we see today may, billions of years from now, slip beyond our event horizon, meaning their light will no longer reach us. Future cosmic observers in our galaxy, or what might be left of it, would perceive a seemingly empty universe outside their local group, a profound change from the rich and bustling cosmos we observe today. Moreover, the acceleration brings into focus the ultimate fate of the universe. If dark energy continues with constant strength, the universe will keep expanding forever at an ever-increasing rate, growing colder and emptier, a scenario known as the heat death. On the other hand, if dark energy changes over time or behaves differently than current models anticipate, alternative fates, such as a big rip, where the fabric of space tears apart, could be possible. But these remain hypotheses awaiting further data. Aside from dark energy, other exotic forms of matter and energy, like dark matter, shape the universe within and near our horizon. Dark matter, an invisible form of matter that interacts gravitationally but not electromagnetically, makes up about 25% of the universe's energy content. It clumps together to form the scaffolding on which ordinary matter accumulates, forming stars and galaxies. While dark matter itself is not observable through emitted or absorbed light, its gravitational effects are measurable, allowing us to map its distribution within the cosmic horizon. Beyond the horizon, what role dark matter plays is less certain purely because we cannot observe its influence there. However, assuming the cosmological principle holds, dark matter would similarly pepper these unseen regions, helping form cosmic structures just as it does within our observable patch. This assumption again highlights the challenge of addressing unknown cosmic regions. We rely on a mixture of observation, theory, and principle to infer their nature. The mystery of what lies beyond the cosmic horizon also intersects with deeper questions about the nature of information and physics itself. For example, the holographic principle, an idea stemming from theoretical physics and quantum gravity studies, suggests that information within a volume of space might be encoded on its boundary surface. Applied cosmologically, this concept leads to intriguing considerations about how information from beyond the cosmic horizon relates to what we observe, and whether limits imposed by horizons affect fundamental physics. Though purely theoretical at this stage, such ideas point towards a rich interplay between cosmology, quantum theory, and the nature of space-time. Understanding cosmic horizons may therefore do more than restrict what we see. It may influence how we understand reality at its most fundamental level. In practice, cosmologists investigate the universe beyond the horizon by examining the shape and statistical properties of the observable universe, looking for subtle signs, or anomalies, that might hint at complex cosmic structures beyond our current reach. For example, patterns in the CMB or large-scale distributions of galaxies could, in principle, reflect influences or boundaries beyond the horizon. So far, these studies have not yielded definitive evidence of unusual features, reinforcing the notion that the observable universe is a typical sample of a much larger cosmos. Still, the limits imposed by the cosmic horizon remind us of the inherent boundaries of empirical science. Our theories about the universe's beginning, composition, and evolution are grounded in observations accessible by telescopes and detectors. Beyond the event horizon lies a realm where our standard tools falter, pushing researchers toward imaginative models, sophisticated mathematics, and inevitably, philosophical reflections on the nature of knowledge. The human quest to understand what lies beyond the cosmic horizon thus continues to evolve, guided both by increasing observational power and by theoretical innovation. New instruments such as large-scale galaxy surveys, gravitational wave detectors, and next-generation microwave observatories aim to refine our picture of the universe's expansion, its energy content and structure. Each advance brings us closer to the horizon's edge, sharpening the line where observation meets the unknown. While the horizon marks a boundary to the visible, it also marks a starting point for curiosity, stretching questions into realms both vast and subtle. By continuing to explore within these limits, scientists gradually paint a fuller picture of the cosmos, including the tantalizing mystery of what lies just outside, forever out of direct sight. While the cosmic horizon defines the limits of what we can observe directly, it does not mark the boundary of existence itself. Rather, it highlights the intricacies of our cosmic circumstances. Beyond shaping the scope of our observations, the horizon also frames how the universe evolves and what future generations of observers might witness, or fail to witness. Understanding this unfolding story involves looking closely at how cosmic expansion and the flow of time intertwine on an immense scale. One noteworthy concept connected to the cosmic horizon is the difference between the particle horizon and the event horizon. The particle horizon corresponds to the limit of the observable universe. It marks the greatest distance from which light could have traveled to us since the Big Bang. Meanwhile, the event horizon defines a more subtle concept. It is a limit beyond which events occurring now can never affect us, even infinitely far into the future. This is due to the accelerating expansion of the universe driven by dark energy. The presence of an event horizon in cosmology means that there are regions of the universe so far away and receding so fast that any light or information they emit from this moment forward will never reach us. In other words, the cosmic event horizon sets a permanent boundary for causal interaction in the future. This is a profound realization, implying that the universe is divided into observable sectors, isolated from each other by the ever-expanding fabric of space. This concept parallels the event horizon around black holes, regions beyond which no information or matter can escape. In the cosmic case, the event horizon is not caused by gravitational collapse but by the expanding geometry of space-time. While the analogy is not perfect, it provides a useful framework for understanding the limits imposed by our accelerating universe. If we consider the long-term fate of our universe under the current understanding of dark energy, as represented in the lambda-cold dark matter lambdictum model, the cosmic event horizon leads to a scenario in which distant galaxies move beyond interaction range, eventually disappearing from view. Over enormous timescales, billions or trillions of years, what is now a rich and diverse cosmic landscape will look increasingly empty to future observers. Only galaxies gravitationally bound to our own Milky Way group will remain visible. This predicted cosmic isolation poses interesting philosophical and scientific dilemmas. Without the light from distant galaxies, future astronomers studying the cosmos might have no direct evidence of the Big Bang or the expanding universe. Our current observational tools, from galaxy redshifts to the cosmic microwave background, CMB, provide compelling evidence for cosmic origins, but these would be inaccessible if lost beyond the event horizon. In a far future where distant galaxies have vanished from view, the universe might appear static or empty to those hypothetical observers, complicating the reconstruction of cosmic history. Because of this, understanding the cosmic horizon is not simply about current observations, but also about developing a comprehensive narrative of the universe's past, present, and future states. It encourages a careful assessment of how cosmic parameters and physical laws shape observable reality over time. Returning to the nearer term, the cosmic horizon also plays a crucial role in the study of cosmic inflation and the earliest moments of the universe. The inflationary epoch, an extremely brief burst of exponential expansion within the first fractions of a second after the Big Bang, set the stage for the universe's large-scale structure, smoothing out initial irregularities and creating conditions that have persisted to this day. Inflation effectively expanded a microscopic region of space to macroscopic scales, pushing parts of the nascent universe far beyond what we can directly observe. These hidden regions, now lying beyond our cosmic horizon, contain imprints of primordial quantum fluctuations magnified by inflation into the seeds of galaxies and clusters. Although we cannot see these regions directly, their influence is indirectly encoded in patterns imprinted across the observable universe, such as the temperature anisotropies of the CMB and the distribution of galaxies. Inflation also raises the possibility that the universe's global structure extends enormously beyond the observable patch, perhaps even infinitely. Some inflationary models propose a multiverse with multiple distinct patches or bubbles, each with different physical constants or properties. While these ideas remain speculative and presently beyond observational testing, they illustrate how the cosmic horizon solidifies the boundary between what we can test and what remains conjectural. To connect these advanced ideas with observable quantities, cosmologists use precise measurements of the CMB, galaxy surveys, and Type Ia supernovae, standard candles used to determine cosmic distances. These observations help refine estimates of fundamental parameters such as the rate of expansion, Hubble constant, the density of dark energy and matter, and the curvature of space. Together, these data constrain how large the observable universe is and strengthen inferences about the unseen regions beyond the horizon. Another aspect of horizons relates to how they shape the flow of information and the fundamental understanding of causality in cosmology. Because information cannot travel faster than light, the cosmic horizon enforces causal limits on the universe. What can interact or influence what? This causality is foundational to physical laws and underpins our ability to predict cosmic evolution and interpret observations. Causality also relates closely to the formation of large structures such as galaxies, superclusters, and voids. These formations arise due to gravitational interactions acting over cosmic timescales and distances. Since no information from beyond the horizon can affect us, structures in our observable universe have evolved within a causally connected portion of space-time. This emphasizes how horizons partition the cosmos into somewhat disconnected cosmic neighborhoods. Scientifically, the nature of the cosmic horizon prompts continuous development in observational techniques and theoretical frameworks. For instance, the study of cosmic neutrinos or gravitational waves opens new windows on epochs and regions traditionally inaccessible via electromagnetic radiation. Gravitational waves, ripples in spacetime caused by cataclysmic events such as black hole mergers, have recently been detected by highly sensitive observatories on Earth and may someday allow us to probe further into cosmic history and the universe's hidden corners. Similarly, neutrinos, elusive particles that rarely interact with matter, permeate the universe and carry information from early cosmic epochs. While they cannot illuminate regions beyond the cosmic horizon now, enhanced detection capabilities may sharpen cosmological models and provide insights into the conditions just after the Big Bang. In terms of extrapolating beyond the horizon, cosmological simulations play an essential role. Using computers, scientists model how galaxies form, evolve, and distribute across large volumes, beginning with initial conditions inferred from cosmological observations. These virtual universes allow researchers to test hypotheses about dark matter, dark energy, and cosmic inflation, and to explore the consequences of various physical assumptions without direct observational data from outside the horizon. Though these simulations provide valuable insights, they inherently rest on assumptions and parameters derived from the observable universe. Hence, the cosmic horizon marks a boundary not only in space, but also in the reliability of predictions, requiring cautious interpretation and openness to revision as new data become available. Overall, the cosmic horizon represents a fundamental limit, imposed by the finite speed of light, cosmic expansion, and the universe's age, that shelters vast regions of the universe from direct scrutiny. While we cannot peer beyond this boundary, understanding its nature has transformed our knowledge of the cosmos, highlighting the intricate connections between space, time, matter, and energy. In grappling with the cosmic horizon's implications, scientists embrace a blend of observation, theory, and rigorous inference. They recognize that while the horizon restricts direct access, it also invites curiosity and innovation, introducing a boundary at the edge of knowledge that constantly challenges our understanding. As technology advances and theories evolve, we look forward to deeper insights into the universe's hidden regions, the laws governing them, and the cosmic dramas playing out just beyond our reach. One of the most profound implications of the cosmic horizon is how it fundamentally limits not only what we observe, but also what we can know about the universe as a whole. This poses philosophical and scientific challenges tied to the notion of empirical completeness, the idea that a scientific theory should ideally explain all phenomena within its domain. Because regions beyond the horizon remain forever out of reach, any cosmological theory must inevitably include an element of inference, hypothesis, and modeling, grounded in data from a limited portion of space-time. This raises an intriguing question. Can we ever truly understand the entire universe, or is our knowledge inevitably bounded by the horizon effects shaped by cosmic expansion and the finite speed of light? Scientists approach this by applying theories such as the cosmological principle, which posits uniformity on scales larger than observable patches, allowing extrapolations beyond the horizon. However, this principle remains, at its core, an assumption, albeit one supported by observations so far, because we cannot test it directly beyond our observational limit. Exploring this further, consider that the observable universe we see today constitutes just a small portion of the full cosmos. Theoretical models and simulations suggest that the overall universe may be vastly larger, possibly spatially infinite, containing a potentially infinite number of galaxies, clusters, and superclusters spread across immense distances. The parts beyond the cosmic horizon may not differ significantly from the observable universe, but their remoteness places them fundamentally outside our empirical reach. This realizes an important scientific and philosophical subtlety. Any cosmological claim about the universe's properties on the largest scales, even the simple statement that the universe is spatially flat or infinite, has underlying uncertainties rooted in the horizon-bound scope of observation. The cosmic horizon effectively defines the frontier of what can be scientifically affirmed and what remains speculative or indirectly inferred. Another critical dimension to this boundary between observed and unobserved regions involves time. Because of the universe's expansion and finite age, the cosmic horizon also serves as a marker of cosmic epochs, revealing not just where but when we see. What lies beyond the particle horizon today might become visible in the future if light from those regions has had sufficient time to travel to us, assuming cosmic expansion does not prevent this. Conversely, the event horizon sets a more stringent future limit on what events can ever influence us. If the acceleration driven by dark energy continues indefinitely, it means that parts of the universe emitting light today might never become visible to us, since the space between is expanding too fast for their signals to catch up. The consequence is that some cosmic regions remain forever isolated, cut off causally and observationally. This paints a picture of the universe breaking into causally disconnected islands, each with its own observable contents but unable to communicate or exchange information across vast expanses. This realization transforms the cosmic horizon from a purely scientific concept into a fundamental boundary shaping the causal structure of the universe. On practical levels, it defines the limits to what can influence or be influenced by any observer located within the cosmos. Such limitations are not merely inconvenient but essential in respecting the rules set by relativity and the finite speed of information transfer. Understanding these causal boundaries also impacts how cosmologists interpret the universe's geometry and topology. While most current evidence supports a spatially flat and infinite universe, alternative topologies, such as those where space wraps around like the surface of a three-dimensional torus, remain conceivable. Within such topologies, an observer might, in principle, see multiple images of the same cosmic objects in different directions, if light circled the universe multiple times. Searching for such repeated patterns or ghost images in cosmic background radiation or galaxy surveys is an ongoing research endeavor. Detecting any such patterns could reveal the universe's global topology and shape beyond our horizon. A failure to find these patterns thus far supports the notion of a very large or even infinite universe without such global shortcuts. But the search continues because the answer has profound implications for the underlying structure of space-time. To improve our understanding despite these boundaries, scientists employ diverse observational strategies and novel types of cosmic messengers beyond traditional light. Gravitational waves, for example, ripples in the fabric of spacetime generated by violent cosmic events like black hole or neutron star collisions, offer a new way to observe the universe. Unlike light, gravitational waves are not scattered or absorbed by intervening matter, potentially allowing observations of regions and epochs previously obscured. Gravitational wave astronomy is still in its infancy, but already provides unique insights into phenomena billions of light-years away. By detecting these ripples, researchers hope to probe the early universe, possibly shedding light on the inflationary period shortly after the Big Bang. However, gravitational waves, like light, are limited by the cosmic horizon. Their detection remains constrained by distance and cosmic expansion, meaning that the horizon still defines where these signals can originate relative to us. Another intriguing tool that complements electromagnetic and gravitational observations is neutrino astronomy. Neutrinos are nearly massless, electrically neutral particles produced in vast numbers in stellar processes and cosmic events. Because they rarely interact with matter, neutrinos travel through the universe nearly unimpeded, carrying information from distant or dense regions inaccessible by light. Improving neutrino detection capabilities may one day allow astronomers to examine epochs and processes within, or just beyond our observable reach. Although neutrinos themselves cannot overcome the fundamental light speed limit or the event horizon distances, their unique properties make them valuable for probing the universe's high-energy environments, such as supernova explosions or the vicinity of black holes. Even with these additional messengers, however, the cosmic horizon remains a fundamental limit. No particle or wave can convey information from beyond it if their signals cannot traverse the exponentially expanding space. Despite this, combining observations from light, gravitational waves, and neutrinos provides a far richer and more complete picture of the cosmos within our observable volume. On the theoretical front, cosmologists continue to explore frameworks that explain cosmic properties and evolution, while accounting for limits imposed by horizons. Quantum cosmology attempts to unify the principles of quantum mechanics with general relativity to describe the universe at its earliest moments and the nature of spacetime itself. Doing so might eventually offer deeper insights into the origins and significance of the cosmic horizon. One concept emerging from these efforts is the holographic principle, inspired by studies of black holes and quantum gravity. This principle suggests that all the information contained within a volume of space can be described entirely by information on its boundary surface. When applied to cosmology, it opens the possibility that information about the universe inside the horizon might be encoded on or related to the boundary defined by the cosmic horizon itself. Though this idea remains speculative and highly abstract, it underscores the deep connections between cosmology, information theory, and fundamental physics. It hints that the cosmic horizon might not only be a limit to observation, but could also play a role in defining the fundamental nature of reality and how information is organized in the universe. In practice, a major focus remains on refining and extending the precision of cosmological measurements within the observable universe to inform our understanding of what lies beyond. Next-generation telescopes and space missions aim to map the distribution of galaxies more comprehensively and to measure the expansion history of the universe with higher accuracy. Facilities targeting high redshifts will observe galaxies formed when the universe was just a few 100 million years old, pushing the boundary of observable spacetime closer to the horizon. Complementary studies of dark energy are especially critical. Since dark energy governs the rate of cosmic acceleration and thus the behavior of the event horizon, understanding its properties will clarify how the cosmic horizon evolves and how accessible the universe will remain in the future. Whether dark energy is a cosmological constant, a fixed energy density of the vacuum, or something dynamic that changes over time impacts not only cosmic destiny, but how the observable universe grows or shrinks. In addition to observational efforts, improved simulations play a vital role in exploring the universe beyond the horizon. These simulations recreate cosmic evolution starting from initial conditions consistent with the Big Bang and inflation, implementing the laws of physics we understand. By examining how structures form and how energy and matter distribute, simulations allow scientists to test hypotheses about the large-scale uniformity of the universe, the role of dark matter and energy, and the implications of various cosmological models. Even though these simulations cannot confirm conditions beyond the horizon, they help check for internal consistency. If the simulations accurately reproduce features we observe, it boosts confidence that extrapolations beyond the horizon using similar physics are reasonable. They also help identify potential observational signatures, such as subtle anisotropies or correlations in the cosmic microwave background, that could hint at unexpected phenomena beyond our current horizon. Nevertheless, the cosmic horizon imposes an enduring boundary on empirical investigation. The inaccessible regions beyond it remind us of inherent limits in science, areas where direct observation fails, and inference or theory must fill gaps. These limits do not denote failure but carve out a frontier for future inquiry and conceptual advancement. Ultimately, the mystery outside our cosmic horizon invites reflection on the nature of science and knowledge itself. It exemplifies how scientific understanding is shaped by observations constrained by physical laws and technological capabilities. It forces us to accept that some cosmic truths may remain forever beyond reach, while simultaneously inspiring methods to glean insight from shadows and clues. In the quest to understand what lies beyond, every new discovery within our horizon sharpens our questions. Each improved measurement of distant galaxies, each refined analysis of the cosmic microwave background, and each detection of gravitational waves or neutrinos pushes the boundary just a fraction farther, expanding our cosmic map. The universe beyond our cosmic horizon, although hidden, is not utterly disconnected from us. It influences the observable universe, shapes its evolution, and beckons with open questions that drive cosmology forward. While it may remain out of sight, the profoundly interconnected nature of spacetime encourages ongoing study with the hope that, through persistent exploration and theoretical insight, we might one day understand the cosmos in ways that reach, at least conceptually, beyond the limits set by the horizon. In this sense, the cosmic horizon is less a barrier than a guidepost, marking both the limits of observation and the threshold of curiosity, inviting us to continue unfolding the universe's story piece by piece, informed by what is seen and inspired by the mysteries just out of reach.